And I think when I hit the record button, you probably saw that come up. And so maybe give me a friendly reminder in the future if we get started on a live lecture and I've forgotten to hit that record button. Um, I've only done that on a couple of occasions this past year. I usually remember about 5 minutes into it when I'm like, oh, time to record stuff. But that's a helpful assist if you ever see that. So today we're just going to kind of ease into ME316 solid mechanics just to talk about the syllabus and then just do some introductory lectures um, on the course content and refresher from Introduction to Solid Mechanics ME216. And I think this is kind of nice. Never really thought about the whole virtual online teaching in the past, but COVID kind of required us to adjust things here in 2020. And now in the summer times when students, you're all off on internships and co-ops, wherever you might be, it makes it easy to knock out a class during the summertime. So it is kind of a neat opportunity now with Zoom to be able to accommodate things like this over the summertime. I think from a ME program standpoint, with senior capstone design, that I think is going to become important with that only starting in the fall. The summer is going to be really helpful for students to get requirements finalized so they're able to start senior design in the fall. But I guess that's enough on that. Let's go ahead and take a look at the syllabus. And so I'll go ahead and share my screen here. And I think we're good with that. Let me move this over on the other side so I can scroll. And I did upload a prior version to D2L here in early May. And I was just looking at that prior to this live lecture, and I realized that was an old description from last summer. It would have been spring of 2020. All of us mechanics faculty got together and evaluated the course descriptions along the mechanics sequence. And so that hadn't been approved by the Board of Regents yet when I taught this last summer, 2020 for solid mechanics. And so when I made the syllabus, I didn't catch that, but I did catch it this morning. And so here is the updated course description for ME316 solid mechanics. We did change the prerequisites, just needing 216 and Math 321. And the main focus on this course is just, again, covering the fundamentals of solid mechanics while emphasizing the distribution of stress and strain. I think in ME216, you're just introduced to the concept of stress and strain, the corresponding stress transformations, strain transformations, and then also looking at, say, axial loading conditions, or you have an average state of stress acting on an axial loaded member. As we get into solid mechanics here, we start looking at things like torsion and beam theory, and we find that stress and strain varies with respect to position along the length of the beam throughout the cross section. And so we'll start to see that distribution of stress and strain as we cover these topics. And so we'll kind of review some of those concepts that you learned in ME216 and review axial loading conditions. From what I tend to recall from past times I've taught ME316 is that you tend not to cover thermal effects in ME216 with the coefficient of thermal expansion. That would cause typically expansion when things are heated up, or contraction when things are cooled down. And so that's kind of a topic we'll touch on as we go through axial loading so that we are able to capture that. Likewise, it's common that statically indeterminate type situations were not covered in ME216. And so we'll look at those statically indeterminate situations as well. That's a situation where your free body diagram just isn't enough to identify what those internal forces are with the free body diagram alone. And so you have to take into account constraints on displacement to identify what those internal forces are. And so following that review of just the fundamentals of 216 and axial loading thermal effects, we'll get into a discussion on torsion, the twisting of materials. We'll look at beam theory. We'll look at combined loadings as opposed to just looking at purely axial loading versus torsion versus beam theory. What happens when you have a combination of those effects taking place? And that really then ties in nicely to what you learned in ME216, where you're looking at the stress and strain at a point. When you have all these different combined effects, you really need to keep track of the states of stress that are being developed by those loadings so that you can then identify what is the state of stress at that point. And so then it ties in nicely to what you learned in ME216. There you were usually given that state of stress and then doing a stress transformation. Now you'll get to learn how to then solve for that state of stress and then can proceed from there. We'll also look at basic failure theories. When materials are subjected to combined loadings, they fail in different manners depending on those loading conditions. And so failure theories are needed to identify how critical that loading state is and what the corresponding factor of safety is. And then we'll also touch on energy methods to calculate displacements, slopes at a point. So that's the updated course description for ME316 solid mechanics. That was approved by the Board of Regents then back in July of 2020. And so that's active now for this summer 2021. But this was in line with what we are covering in ME316 now. And just everyone here, I see we've gotten a few more that have joined in, but I'm Jason Ash, a faculty member here in mechanical engineering. My office is just to the left of the main ME office, back in a few office areas back there in CM 128. Office hours, kind of what I did during the summertime when we had a smaller group of students is just have Zoom visits by appointment. We have our normal live lecture from 9 to 11. And so generally I'd be fine visiting with students here after class, but just feel free to email and identify a time that works for you to visit. With a number of students working full-time during the day, 8 to 5, I also found that sometimes evening visits were necessary last summer, which is totally fine. I have my office phone and email. I am still in the office quite a bit, so you can contact me there. Well, let's see, textbook. We're still using the Hibbler textbook that you use for ME216. So if you have that, you're good. I always do the first day access since a lot of this stuff is being done online virtually. I figured that might be necessary if you didn't have a copy of the textbook so that you could have access to that electronically. But the first day access is not necessary. All you need is the 10th edition textbook in whatever format, and you'll be fine with the course. We won't do any type of online homework or quizzes through first day access at all. So it's really just the textbook that's needed. For the homework, I'll just assign that here in D2L, and then I'll have you just do problems from the textbook on engineering paper, nice, neat, given, find analysis, and then scan that in as a PDF file so that you can upload it to D2L. And then I just grade and evaluate that through D2L online. And with that, I think the students have been doing really well, say this last semester or so, and scanning those in a nice PDF format so that it's easy to print out. Typically for your homework, I'm not going to print those things out, but for exams, I do like to print those out and grade them by hand and then scan those in to upload to D2L. So do kind of take that into account in terms of scanning things in so that they're easy to see and that I could print those out if I wanted to, and it wouldn't take a ton of toner to do so. The similar thing would be the lecture notes that I'm posting. If they're uploading similarly to that, that would work perfectly for me. And so this one for the summer, again, is online asynchronous. And so all of our course content will be saved to D2L. I'll post our lecture notes. Typically, I'll try to do that in advance of the class. And then following class, I will upload the live lecture video for those that aren't able to join in live. Monday, Wednesday, Friday, 9 to 11. That's when we'll do the live lecture. And main thing, I think all of you are pros now at using D2L, so you're all set there. But I guess, are there any questions so far at all? And again, with Zoom, you can always press down on the space bar if you have a question. That'll turn your microphone on, or you can just unmute yourself if you ever have any questions. As far as grading is concerned, there's going to be 2 exams throughout the summer months here that'll account for 50% of the grade. Homework is 10%. Either 1 or 2 projects, that'll be 15%. And then we'll have a comprehensive final at the end of the summer that'll count for 25% of the grade. The grading scale is indicated, and mainly the objective is really to develop a firm understanding of stress and strain analysis, continuing on what you learned from ME 216. And we have the whole list of course outcomes looking at applying equilibrium, compatibility, and constitutive relationships to solve our mechanics type problems. We'll evaluate bending, shear, and axial stress. Looking at static impact loading conditions, we might get to that. That shows up in the discussion on energy methods. And so we might have some time to look at that. Looking at failure criteria for that 4th item. And there's a couple alternatives. We'll probably get into that more as we get to our lecture notes, but there's a couple ways to tackle that concept. Evaluate stress and strain for various types of loading. Determine deformations and rotations using energy methods. And we'll also look at, in addition, the internal pressure vessels and the combined state of stress caused by internal pressure vessels. What I found last summer when I was putting the syllabus together is that we cover quite a bit of material in a short time frame. And so in terms of expectations, kind of think about for every 1 hour class period, it's expected that you spend between 2 and 3 hours in reading and solving the homework problems. And so we're meeting 6 hours a week typically. And so that's going to be anywhere between 12 to 18 hours in doing stuff outside of class for a 3-credit summer course. And so it is a lot of information in a short time frame. But the students last summer handled that really well. And what I really like to do is try to get the homework out there and timed with the lectures, so it makes it easy to do those things as they come along. The main thing for you as students is just make sure to keep up and do the homework as quickly as possible, because it would be very difficult to try to catch up if you get behind. And I think that 12 to 18 hours is a pretty good estimate. I did have another advisee take like 3 classes last summer so that they could start senior design in the fall. And I kind of gave them a warning or a heads up prior to that. I was like, you probably should anticipate spending about 60 hours a week if you want to tackle 3 classes. And they gave that indication that that was about the right time frame, the amount of time they spent on a weekly basis. So they were kind of good to get, they were glad to get the heads up that it was going to be a bit of an undertaking to take 3 courses. Maybe I could just pull you guys too and see how many classes you have. My screen's a little different than what it usually is at school. Oh, I can add a question. Let's do that. There we go. So I did make this anonymous. So I think we're good there. I did make a poll. It will probably show up in D2L, I think. If not, I'll do that later in D2L and have that sent to you. But I was just kind of wanting to get an idea of how many classes y'all are taking. I'm not sure if that came up as I was anticipating. I hit the poll button. Did you happen to see that come through?
No, I didn't see a thing come through.
Okay, no worries. I know how to do the polls in D2L, so I'll just kind of send that and you'll get an email. We only have probably a fraction of the students on here today, so we'll be able to do that here after class. But I'll just kind of get an idea then from that anonymous poll how many classes each of you are in. And we'll do that through D2L. That'll work out well. Then there's just all the other stuff on the student effort. For my classes, I have a 10% penalty for each class period that homework is late. But kind of as I mentioned before, we cover a lot of material here during the summertime. So I would definitely recommend just keeping up with homework and not getting behind, because it would be very difficult to catch up. And then likewise, this all be done through D2L. And I make the deadlines due for that at 11:59 p.m. So that you have time in the evening to finish that up if needed. I said that in the email too, that I normally would make homework due on Fridays at midnight during a normal semester, but last summer we had some students that requested that be moved to Saturday by 11:59 p.m. since they were working all week, and that was totally fine with me. That didn't make any difference. So keep me posted on that, just with the summer situation. If we're maybe needing to shift the deadline for the class as a whole. Everything that we'll do through Zoom, online, through D2L, again, we're just essentially using the honor system to maintain our academic integrity. I think what I found since we had to switch over to online in March of 2020 is that students have been doing really good with that. I really haven't seen any concerns come up with that at all. The exams, those are take home as well. And I just have you sign a statement saying you only use the allowed resources with our D2L pages, your textbooks and things like that, and that you're just doing the exams by yourself. And so I've been really satisfied with the students and their academic integrity throughout this whole situation. And then as we continue through the syllabus, we just have the information on the course being online asynchronous. There's the ADA information, freedom and learning statement that you're probably all aware of, electronic device policy. And I think the main thing with Zoom is just making sure you have your microphone muted when you're not talking. And then you can either unmute by clicking unmute, or you can hold down the space bar when you have a question. By default, I have it set up so it doesn't show your video in Zoom. Mainly, you might be waking up in the morning and you don't want to share your video and you don't want it to default to that. But if you want to share your video, that's kind of nice to see people when I'm teaching, but that's completely up to you. There's the Title IX information and the copyright information for the course. So you'll be able to read through all that. I did keep the COVID-19 information in here, just that they were requiring us to do this past year, but that's something we probably don't have to be concerned with at all here over the summer for an online course. And then thankfully, for those of us that are on campus, May 10th is when the Board of Regents remove the mask policy. So we no longer have to wear masks indoors, which is super exciting. The thing that's of more interest is really looking at the schedule for this summer. And this is kind of where we get to see that, yeah, it is fairly quick how we go through the course material. And so this week, again, we'll just do an introduction review of both statics and the intro to solid mechanics. We'll continue that looking at chapters 1 through 3 and 9 through 10. And then we'll review axial loading conditions here towards the end of the week. Next week, we'll cover torsion in about a week. And then we'll get into beam bending following that. And it is just going to kind of depend on how we're moving along when we introduce that exam one, and when that'll be due. And so it'll be around that time frame of June 25th. What I really liked is having that first exam before the 4th of July holiday. And then following that, we'll finish up beam bending and get into transverse shear stress of beams. Then it works well to go forward a little bit in the textbook and then talk about the deflections of beams and shafts, before then coming back and looking at theories for failure, pressure vessels, and all that stuff, combined loading conditions. So we'll have our second exam around the July 16th timeframe. That will essentially cover through beam bending. And then the final exam will be towards the end of July timeframe. But that's it for our syllabus. Are there any questions at all over the syllabus? I think I'm going to exit out of here then. And then go over here to our lecture notes for today. And so last summer, I did kind of rewrite a lot of these lecture notes so they're easier for you to read. They're always okay for me to read and to do our writing on the board for students, but I had to rewrite some of these so that it was easy for others to read. And so with our introductory lecture, we're just going to talk about really more the fundamentals of solid mechanics and reviewing what we learned previously in statics. I'll touch a little bit on dynamics and mechanics of materials. But another course that you've probably completed already or in the process of is product development. And so it kind of helps to couch the whole concept of mechanics into thinking about that from a product development perspective. And as you go through the design process, really the bottom line for a design engineer is what materials should you use in that process, and then what is the size and shape of that material. And so typically the goal is then to minimize the amount of material that's needed. That's going to reduce the weight of the product that you're going to be designing. As you reduce that weight, again, you have less materials, so your stress levels are going to increase, and so you're finding that optimum balance in terms of maintaining the safety factors that are desired in your design, while minimizing the amount of material in the process. That really becomes important with things that are in motion. To cause that acceleration, you need more force. If it has more mass. And so you can really save on fuel economy the lighter you make those systems. And I think two of those, both of those, what materials should be used, what is the size and shape. There was a good senior design project that related to both of those requirements. It was the automated fishing pole casting device for quadriplegic individuals. The senior design team that was doing the design for that, they did a really good job on their dynamic analysis with the rigid body rotation of the fishing pole, and on the mechanics of that whole process. But then the housing for that, they had put a little bit of less thought into the housing to contain everything. And so prior to their critical design review, well, one of the team members, I think a couple of the team members stopped in, and they're like, well, we kind of finished designing this housing material for it. And the only problem that we're seeing is like SolidWorks is telling us that it's going to be about 30 pounds. And we want to make this thing kind of portable so it's easy to take to a dock or something like that to go fishing. And I was like, well, let's take a look and see what's going on there. And if I remember right, for their housing, they had like a 1/4 inch thick sheet of steel on the bottom of it, for the bottom of the housing and then the sides. And I was like, well, that's a pretty sizable chunk of steel that you have there. And so a couple of things, what material should be used? If you're using this for fishing, you're going to obviously be around water. And so there's concern on the corrosion aspects of using steel for that application. And then size and shape, with that big, thick sheet of steel, I was kind of like, I'm not sure if this thing is meant to be bulletproof, but I'm sure it would be if you had a 1/4 inch thick sheet of steel, and that's where the chunk of your weight is coming from. And so we talked about that, and just like, you could probably be fine with just some aluminum sheet metal that you bend into the housing material and be at probably a fraction of the total mass, probably 10%. And you're still going to be fine for just the structural viability of it. And I think what the team then did at that point is they did do some finite element analysis to just look at the stresses that are being developed. And they did confirm with that 1/4 inch sheet of steel as their base that they had a factor of safety of around 100. And so it was definitely built to withstand some brutal forces in that regard. And so they did end up going with an aluminum sheet metal, and it worked out nicely. They ended up placing second in their regional competition that was held. But that kind of just touches nicely on really that need to identify the material that should be used for the application. And then mechanics is really what helps you define what is the size and shape. If you have a factor of safety that is required for the design codes, then you can use your mechanics analysis to achieve those factors of safety in your design. But there are a whole host of other factors that design engineers really need to consider. Again, really the functional requirements, what is this system supposed to do? And so when you design that, the goal is to be able to meet those tasks, those functional requirements. Additionally, you're looking at designing that in a way that's easy to be manufactured. And I'm really glad Dr. Lally now teaches his ME 120 6L, the design for manufacturability. That way, first year students really start thinking about that their first year on that whole concept. If you can make a product that is much easier to manufacture, those costs are going to go down tremendously on the manufacturing end, which helps on the profit end of things. And that's good then from an engineering standpoint to kind of realize that insight that can be provided by those in the manufacturing area, machinists, things like that, and developing a good rapport with them on designs that you are developing. It's always good to run those things by the machinist to get their input, because they definitely have that background and can offer insight into things that could improve things and the manufacturability of those systems. At the same time, you're developing that relationship with the machinists, the manufacturers, and so I think when you have that, they definitely want to work well with you and help you meet your deadlines and things like that, as opposed to a situation where you may not have that rapport. It'll get done eventually, but it might not come to the top of the list. When I worked at Hutchinson Technology in Sioux Falls, that was a pretty involved process going through design. You did have to, once you had your design, you had to visit with the machinist area, the manufacturing area, quality area, get sign off by all the managers on that. And so it was visiting with a few different groups to just verify things were being designed properly so it's easy to manufacture, and everybody was good with it. Other factors: consumer information, human factors, how are people going to interact with this product, and how can we design that so that interaction is done safely. For the presses that we had there at Hutchinson Technology, those were all pneumatically operated by air, and that's really an OSHA requirement. To block the air, you had to use both hands to block the air channels on each side, and then that would initiate the press coming downward. So they didn't want a situation where you just had to use one hand to initiate the press coming down. They had to use both hands, so you didn't have a free hand out there in La La Land getting crushed by a press. But the same is true and just how people interact with the products. Marketability, looking at advertising and packaging those things. That's really interesting if you're just buying some mundane item like a toaster. If you're looking, say at Walmart or Target or something, you can kind of get an idea of, wow, they put a lot of effort into the packaging, showing the details on the outside of that to make it appealing for the consumer to purchase. So that's taken into consideration. Environmental factors with the making of the product, trying to do that in an environmentally friendly manner, looking at using and then retiring that product eventually. Quality, just looking at the general quality of the material itself. Is it a uniform material properties throughout? Looking at the tolerances that are needed so that it's able to meet the functional requirements. And then looking at overall product life, maintenance, safety, reliability, operational economy. I think those that have done maintenance on vehicles have likely have stories that you kind of see things that are like, you know, that would have been a lot easier if the engineer would have done this. When I was in high school, I had an old Dodge Omni, and to change the timing belt on that, the bolts that were taken off, one of the bolts went through the water jacket, so you had to drain the radiator to replace the timing belt. And also one of the bolts, you could almost get it off, but it backed into the frame. So you had to take the bolts off the engine mounts and just use a hydraulic jack to lower the engine a bit so that you could back that one bolt out. But just little things like that makes it a little bit more difficult to change a component on there. Saw the same thing with the Dodge Caravan that we have. When replacing the water pump, there's probably a half a dozen or so bolts holding that on, and only one of them, you couldn't get out because it backed into the frame. So I had to lower the engine for that one too. But that was kind of a positive because I needed to replace the spark plugs too. And so getting to the back three was a lot easier when the engine was lowered about a couple inches. So that was a bonus. I changed the spark plugs while the sealant was curing on the water pump. So there are some benefits there. But from a design perspective, oftentimes that really comes down to cost. That's really what you're trying to do. And that overall decision-making process is minimize the cost as much as possible so that you can focus more on the profits that are being made. But those are all factors. There's many more that need to be considered throughout that design process as from a design engineer for that product development process. But kind of my perspective is it's nice that you're able to see that product development process in ME 265. But now as you're going through all your ME 300 level courses, you're now gaining the engineering fundamentals that are needed to analyze those designs. And it really should be the analysis that ultimately drives that design, so that you have the engineering fundamentals to back up that the product, the system will operate as intended when it's finished. And so that's really the ideal goal of engineering, is to be able to utilize the analysis to have confidence that the system is going to be working when finished. And testing gets placed in there too, because you still need to have that verification that things are behaving as you expected through that design process. NASA, JPL, they do that with the rovers that they send to Mars. They run them through batteries of tests here on Earth. And so that when they send those to Mars, their goal is to have all the kinks worked out, because it's not easy to make any repairs once it's on the surface of Mars. And they have a pretty good track record of making very reliable systems to rove around on Mars. I think it was probably about the 2003 timeframe is when they sent Spirit and Opportunity to the surface of Mars. And I think they originally were planning to have like maybe a 6 month to a year life for those rovers. And they continued to rove around for over a decade. It was amazing how long Spirit and Opportunity clung on there, collecting scientific data. So pretty neat stuff. Brett Kennedy, he was one of the chief systems engineers at JPL. He gave a guest lecture at one of the ASME student professional development conferences. They call them engineering festivals now. But it was about an hour and a half to 2 hour presentation that he gave on the systems engineering design of spirit and opportunity. And let's see, at that time, what they were doing is when it was coming into the Martian atmosphere, they were doing the ignitions to slow it down, and then eventually the bouncy ball approach to landing on Mars, and then opening up from there. But throughout that whole process, if the timing wasn't quite right, they anticipated that they might see upwards of 30 G-force. And so they really designed Spirit and Opportunity to withstand 30 Gs along that whole impact. And I think one of them experienced 2 Gs and the other one experienced 4 Gs during the landing. And so they definitely were well designed, well beyond that. And so that might be one of the reasons why they survived for so long, because they were built to withstand 30 Gs, and the most they ever saw was 4 Gs in that process. And so from a solid mechanics approach, there's 2 main concerns that we have to deal with. One is strength. Can the material strength sustain the loading that's applied to it? And then 2, stiffness. Are the deformations acceptable? And you really need to consider both when you're going through the design process. For the stiffness, for example, if the system or a part of that system deflects too far, and it's a moving system, if it deflects too far where it then causes an interference and collision with another component within the system, that's going to lead to a failure. And strength, if it breaks, it's probably not going to work. And that becomes interesting when you start talking about composite materials, because you can have all sorts of different failures start to occur, like interlaminar failures and other types of failures where it's still together, but things are happening. And so I think one of the funniest definitions I've heard of failures is you can really define failure when you have 2 pieces instead of one that was intended. So it's discussion there in that process, but the question might be is how much damage can you have from, say, a composite failure before it's unable to meet its functional requirements, type of deal. And so generally these are 2 separate things that are considered. The 2 different criteria that you have to meet, but there are occasions where you have to kind of look at those simultaneously in that process. And then just reviewing a bit about the fundamental principles of solid mechanics, we really have 3 main tools to answer those questions on strength and stiffness. One, we have equilibrium that we've been learning since ME 110, and then statics and intro to solid mechanics, where our main tool that we use there is our free body diagram, really to look at our component or system. What are the forces acting on it? What are the reactions that are occurring to keep that in place? And doing our summation of forces and moments equal to 0 to determine what those internal loadings are. And that's for a system then at rest. And so one of the things that you see in your solid mechanics textbook, and then when you get into machine design, a lot of those systems that you're going through and designing for are for things at rest. And the textbooks really don't do or focus a lot on looking then at systems in motion. And so we'll talk about that here a little bit towards the end. 2, there's compatibility. that's where you're starting to look at those statically indeterminate situations where you need to look at the displacements to make sure they're matching up. You're looking at continuity. Y prime would be your slope, Y double prime would be your curvature. And so those would also have to match up at um, uh, a certain point so that those are not violated. And then 3, you have your constitutive relationships, really how you relate stress to strain. And you really have looked at Hooke's law, probably both in ME 216 and MET 231, 232 if you've taken that. And they generally will start that introduction with a 1D Hooke's law, where your stress sigma is equal to the Young's modulus, capital E, times the strain, epsilon. But we'll show you the full 3D Hooke's law. That's the one I prefer to remember, because generally when we're looking at solid mechanics stuff, it's a 3D state of stress that we're dealing with. So we need to use 3D Hooke's law to have a valid constitutive relationship for that. But all 3 of these then are tools to solve for stress and strain. The big concern that I just mentioned is, what about bodies in motion? Again, we learn about this in dynamics, where we have summation of forces equal to mass times acceleration, and summation of moments is equal to I of m times alpha. In dynamics, you might have seen this as I alpha. I do like subscripting that with an m to really designate that as the mass moment of inertia. And that's really a body's resistance to a change in angular motion. We use a I value in our ME 316 solid mechanics course, which is area moment of inertia. And that's more of a resistance to bending. And so I like this M designation here for bodies in motion. So it doesn't cause confusion with our I value that we use frequently here in solid mechanics for the area moment of inertia. But again, this dynamic stuff is largely ignored in solid mechanics and in also machine design texts. They do touch on that a little bit with impact loading. Impact loading really just involves looking at kinetic and potential energy in that process and identifying a kind of impact factor to look at a quasi-static approach to solving those problems. And then fatigue looks at cyclic loading, but that's still not bringing into the dynamics of the situation. It's just looking at how many cycles that's going through. But the main thing that I kind of stress here at this point is that really that's what dynamics is needed for. It's that same process that you go through with solving these systems of equations to determine what your internal forces are for bodies in motion. And so the process is the same. And so I think that's why you find that this is largely ignored in the solid mechanics textbooks, because once you apply your dynamics principles, you end up with those same quantities that you're interested in, just the internal forces and moments for that. And then your solution process follows the same as if it were a static situation. Another thing that's helpful then from a dynamic situation is if you look at mechanical vibrations. That's one of the electives that you could potentially take as a senior. That then starts to look more at these dynamic effects, and instead of just doing kind of a quasi-static looking at potential kinetic type energies, it really takes you more through Vibrations will take you more through that aspect of looking at the system of equations, solving those from a differential equations perspective to determine what that response of the system is from a dynamic loading situation. And there, then you will be able to see the maximum forces that are experienced during those dynamic loading situations. Well, let's talk about then the solution process that you go through when you're solving these types of equations or these types of problems involving mechanics. First step always is just that problem formulation, where you're identifying what is known for the problem, what is given, and then what you're wanting to find. And so given, find, you really want to define those clearly so that you know what you're trying to solve. And those are laid out nicely in the problems in the textbook. But if you're solving a problem on your internship or co-op, you don't have a nice, neat problem statement to work from. And so you're doing those steps yourself, looking at what are we trying to accomplish here with the design? What are some known factors? What are some known specifications that we need to meet? And then again, what are we trying to resolve in this process? You have that, and then you can start making use of your analysis tools. And first thing that you generally do is set up your equilibrium equations by drawing your free body diagram, FBD. You can look at the reaction forces for that system free body diagram. Can you identify what the reaction forces are based on that? If so, you're set. You can solve those. Then you can draw additional free body diagrams of specific components and then determine what the internal forces are. And then you're set to proceed from there with your equations. And then 3, are there enough equations for the number of unknowns you have? And then if that's yes, it's statically determinate. If no, it's statically indeterminate. And then also I put in that note on dynamics. And so in addition to free body diagrams, if you're dealing with the dynamic system, you would also need your mass acceleration diagram. This is the acronym I preferred, is the MAD diagram. As you went through dynamics, you found that when the right-hand side is not equal to 0, 0 for statically loaded systems, and it's now a system in motion, that the right-hand side not equal to 0 makes things a lot more difficult. So mass acceleration diagram is the acronym I preferred, but I also know that that diagram is often referred to as the kinetic diagram, showing the accelerations on the system. And so that could be important, that mass acceleration diagram, if you are dealing with a system in motion. But again, if you have with your equilibrium equations, your equations of motion, if you have enough equations for the number of unknowns, that is a statically determinate case, which means that you know all your internal forces and can solve those with your equilibrium equations. And so you can solve your internal forces, which means you can solve your stress, your internal stresses. Once you know stress and you have your constitutive relationship, you can solve for strain easily, and you can review the solution. The problem with the no side, the statically indeterminate side, is that just with your free body diagram alone and your equilibrium equations, you don't have enough equations for the number of unknowns that you have for the system. And so you then need to really add more equations with respect to compatibility, really your constraints on displacement, slopes, things like that. And so you're now adding more equations, relating those unknowns to one another. And so that then becomes a situation where you're solving the stress and strain together simultaneously. That's a little bit more difficult because it's not just plug and chug in terms of statically determinate where you're solving for stress and strain. Since you're solving a system of equations, that's a little bit more complex for the statically indeterminate cases. But same thing, you want to review the solution to make sure it makes sense. And what you'll typically find is that for your statically indeterminate cases, it's easy to make mistakes throughout that process. And so if you review the solution, plugging your answers into all your different equations that have developed, you should be able to see if you've made a mistake. You'll have something that shows up that's not equal to one another, which would be odd. So that can help you identify if you've made a mistake along the way. And hold on just a second. I guess any questions so far? The whole idea there then is that you want your stress to always be less than the strength of the material, otherwise it's going to fail. Additionally, I'm sure that factor of safety concept was introduced in ME 216. Generally, you're going to want to have a factor of safety that you're trying to design to make sure you reach that requirement. And then the displacements that you're solving from the resulting strains are those less than what is allowed, so it doesn't cause any interferences, that type of thing. And then we only have, I guess we have a couple more pages. So I think this is not going to take too long with reviewing that. So we'll be able to finish up a little bit early today. But just looking at classification of forces, there's things that are grouped into what are called surface forces or contact type forces. One is a concentrated load, just a force acting at a point. It's going to have units of newtons if you're in the SI system, or pounds if you're in the US system. Distributed loads defined as W, which is a force per unit length. And what's oftentimes helpful with that is when you're drawing your overall free body diagram to figure out reaction forces, you can find an equivalent concentrated load. And so if you have a uniform distributed load over a given length, the equivalent concentrated load would be just that distributed load times the length, and it would be located halfway along the length of the beam at that point, since it's evenly distributed. And so that works to find your reaction forces. But then when you want to find your internal loadings, you do have to draw a free body diagram of just that portion and including the distributed load over that portion. But at the same time, then you can do that same trick and figure out what an equivalent concentrated force is, but it would just be over that small section. We'll go into detail on that when we get into beams, but we do need to typically find these equivalent concentrated loads in terms of solving problems. Other situations you might have is, say, a triangularly distributed load where the loading decreases with respect to length in a triangular fashion. And so we have the maximum load per unit length at the far left, W, and that decays down to 0 at the far end. This is common, say, for hydrostatic type loading in a fluid. And with that, the equivalent concentrated load is really just, again, this area of the triangle. So WL times L over 2. And you can see that was the same here. It's just the area that's generated here, W times L. But for this case, the equilibrium point is a third of the distance over from that heavily loaded side. And what that's meaning is if you were to sum moments, then about L over 3, you would be within equilibrium at that L over 3 point. Summation of moments would be equal to 0 there at that point for that loading distribution. So there's distributed load, and then there's surface tractions, which is a force per unit area. And the easiest way to think about surface tractions is if you've done tensile testing where you're gripping on a sample and pulling on it at that point. Wedge grips are nice in that as they're extending and placing more force on there, it causes more pressure to be placed on the sample itself. And so that pressure times the area would give you essentially the force, and then that vertical would be that force times the frictional coefficient would be the net force acting upward. But it's a force per unit area that's causing that that pressure with the surface and developing then a surface traction. Those are all contact forces. Then there's non-contact forces named body forces. Weight is a good example of that, and that's something I cover in ME 110. Weight is equal to mass times gravity divided by G sub C. This is something I cover in ME 110, that dimensional constant. And now in these courses, you start to see that in fluid mechanics when you're talking about mass flow rates and things like that. If you come across those situations, make sure to take into account G sub C. If they give you a mass flow rate of, say, a pound mass per second type deal, you'd have to divide through by G sub C to get that into a force if you're doing a force type equations. And so let me know if you ever need any refreshers on that. But when I covered that, it's really anytime you're dealing with a mass or a mass flow rate, a mass density, those types of things, you really need to take into account that G sub C when you're dealing with the US system. I think I was teaching solid mechanics 1 semester about a half a decade ago, and so students just came from a fluid mechanics test, and they're like, "I remember you talked about units back in ME 110, and we just had a fluid mechanics test. Most of our homework was SI units, so we didn't have to worry about it, but our exam had US units," and they asked about that dimensional constant, if they did that right. And so there's other forms of body forces. Electromagnetic inertia can be considered in with that, with the mass times acceleration, and the rotational I of m times alpha. And so next up are the reaction forces. These are the forces and moments due to boundary conditions that prevent movement. And that's something you looked at last year as well, looking at reaction forces. And really, all 3 of those are considered external forces. So we have contact type forces, non-contact and reaction forces. Those are all external forces. And then you have your internal forces, the loading that happens within the members. Let's take a quick 5-minute break. I hear some noise going on. Somebody might be knocking And so I'll be back here in just a second. Sorry about that. I think everybody's here. All right, it hasn't been 5 minutes yet, so did you want to mark yes if you're ready to finish up here? Or some of you might have taken a break, so I'll just make sure everybody's back before we continue on. Yeah, the dogs were barking pretty crazy, so I wanted to see if they needed any help, but all was good. But I think me coming upstairs helped calm the dogs down a little bit, so that was good. All right, so I think we'll go ahead and finish up here. And where we're at, we're just discussing the internal forces and the positive convention of those internal forces, say, within a beam. This is something you'll find in your Hibbler book, the convention that they use, but it really helps maintain that correct sign in calculating deflections. And so if we consider a beam, for example, this would be a simply supported beam with a pin on the left at point A and a roller on the bottom of point B with a force in the middle there. Remember, for pin type reactions, it can support both the force in the X and the Y direction, whereas a roller can only support a force in the Y direction. One interesting thing about your Hibbler textbook is that they really don't give any stipulation on which direction that vertical force has to act. From a physical standpoint, if you have a beam, a roller could only provide a force in one direction. It can't, if it's not secured to that, it wouldn't be able to provide a downward force. But I think Hibbler has the mindset, well, you could put the roller on the top if you needed to, if the forces were in such a situation where it was going to be deflecting upwards at that point. And so that's the main thing to be aware of from Hibbler, is that a roller can provide any type of vertical force, whether that be vertically upward or a downward force. But from a realistic standpoint, take that into consideration. The roller that you've provided, is it able to provide the reaction force that's needed? Now, when we start doing a free body diagram and we cut into that beam to look at a section of that, we need to then identify what the proper notation is for the internal shear, bending moment, and internal load. And so we have A of X and A of Y still are reaction forces that could be supported by the pin loading condition. And for the internal positive convention here on right side of a cut, a positive shear force is acting downward, and a positive moment is acting counterclockwise. Axial loading, it's always positive away from the cut. And so then if we look at on the left side of a cut, we know Newton's third law, every action has an equal and opposite reaction. And so those internal forces would be acting in the opposite direction, shear upward, moment clockwise, and a normal force P acting to the left. And so it depends on the textbook that you're using. Sometimes or oftentimes they'll use a P to define this axial load. Other times it'll be a capital N to define the normal force. And so it's just a matter of the notation that your textbook uses. For axial loading conditions, you probably remember the average stress is equal to P over A, the load over the cross-sectional area. But then other textbooks will use an N for a normal force as well. The thing I dislike a little bit about using N for normal force is that when you're solving for that, say in the SI system, the normal force is measured in newtons, and so you're solving N, and you have N as a unit then as well too. So I think the P works a little bit better from that standpoint, where that's not going to match your units then, or cause confusion with your units. But then this P can be problematic when you start dealing with situations that also involve pressure, because then you have a lower P for that. So it's mainly just kind of keeping track of that stuff. But again, there's reasons for the positive definition. I think the easiest one to notice there is the internal forces. If the internal force is positive, it means that it's being stretched or is in tension. And if P is negative, it means the forces are acting in the opposite direction, which means it's in compression. But the positive convention is very important to follow, really, when you start looking at the displacement analysis and understanding the stress. As you get into that chapter 12 on the displacements of beams, and when you get into energy methods, if you don't draw your free body diagram correctly for your internal forces, that can lead you to the wrong magnitude in solving for that. And so if solution is positive, then direction is correct as indicated. If solution is negative, then it acts in the opposite direction, but that's okay. You want to retain the sign in your answer and your solution process for the resulting displacements to come out correctly. And so the last little bit of discussion is just, what about those inertia body forces looking at dynamics? And so I've kind of just gave an example of that to really help you make that connection between what you've learned in dynamics ME 221 and along with what we're learning on this mechanics track. Just how you would set up a problem associated with that. But if you're given a propeller with a angular velocity, omega radians per second, and alpha angular acceleration radians per second squared, say we have a propeller that's spinning around, we can still make a free body diagram and mass acceleration diagram of, say, the right-hand side of this. And we can follow our convention that we've defined. On the left side of the cut here, P would be acting to the left. We'd have a clockwise moment, shear acting vertically upward, and then the weight acting down at that section as well. And I have the tangential direction and normal direction defined in relation to that portion of the propeller blade. For the mass acceleration diagram or kinetic diagram, you'd have your mass times your normal acceleration and your mass times your tangential acceleration. And I would have to remember that relationship to omega and alpha from dynamics there. If I remember right, it's something like omega squared r for A of n and alpha times r for A sub t. I'd have to double check that though. It's been a long time since I've taught dynamics. So those are the two translational type accelerations. Then you also have the IO times alpha, your angular acceleration there. But that with your free body diagram, then you can sum forces in your normal direction. That would be equal to P and equal to mass times your normal acceleration, your tangential set acceleration, your weight minus V, positive down, is equal to MAT, and your summation of moments about the origin would be equal to IO alpha. And so that gives you really your systems of equations, and it gives you then a means to solve for P and V there. And then you could also, with this one, I didn't show that in terms of M, but solve for your internal moment that's being generated as well. But the main gist of everything here is that you really need to know what your internal loadings are to determine what the internal stresses are. And so that's really that connection back to dynamics if you are dealing with a system in motion. The other thing that I wanted to touch on that I skipped over was our internal shear. What I've done here is used a capital V with horizontal lines on the top. What I wanted to do there was really signify that as an internal force, a transverse force. As we get into beam bending, we'll be dealing with the displacements, and those are commonly referred to as UV and W. And so U would represent a displacement in the X direction, V would represent a displacement in the Y direction, and a W would represent a displacement in the Z direction if you're working in 3 dimensions. And so that vertical deflection is a lowercase v then. And so I really like having the transverse shear force designated with the capital with the vertical lines, so it doesn't cause confusion with the vertical displacement, which is a lowercase v. And so I'll follow that notation throughout the semester so that we can avoid that confusion. Another thing that I mentioned is W being the displacement in the Z direction. That starts to show up when you start dealing with plates and shells. But we find another complication in that W is also used to define the distributed load. And so for our course, we're not dealing with plates and shells at all. So anytime we refer to a W, it's going to be in regard to distributed load. But the first time I was dealing with a plate and shell, and I was looking at row arcs formulas for stress and strain, they were defining a W in an equation. And I'm like, this does not have any relationship to a distributed load. What the heck are they doing? And it took me about 10 minutes to realize they were just talking about the displacement in the Z direction. I was like, okay, that's a little confusing. So be aware of that as well. I think there's another spot here in the semester where I bring that up. But that was a little bit longer than I had intended for our first day, but we did make it through those lecture notes. I'll go ahead and stop sharing that. Are there any questions at all from what we've discussed today?
No, I don't have any questions.
Okay, perfect. And did you guys hear the dogs barking at all?
I didn't.
Okay, that's good.
I didn't hear them either.
Perfect. Yep. I was kind of concerned about that because that would have been a little distracting. They were only barking for a little bit right before I kind of stopped it for a second. But they've been pretty quiet since I made it back. That kind of calmed them down when I went upstairs. They're 2 Pekingese dogs, Riley and Roxy. And they're really calm when it's just us. But with the contractors working on the house and things like that, they're a little stressed out and they like to bark during that. So apologies on that. Were there any other questions at all? All right, well, thank you so much for your time. I'll get the updated syllabus posted to D2L and then also today's video. There's no homework quite yet. We're just doing a review today. We'll probably get a homework assignment together by Wednesday or Friday. So that'll be due next week timeframe. But thanks for your time today, and we'll see you on Wednesday. Have a great rest of your day.